and I take any real number, I produce another force. Okay? And these two things match. What are these equations saying? It is giving some conditions on these two processes. Okay? Alright? The first one, let's come to the first one. Remember, taking two things. So firstly, we need to start up.
It's not much because people asking questions and all that, but I mean, I think when they put up the videos.
ETA, please mute your microphone. So, now, so we need to start up with a set, okay, which is the collection of all our vectors that we might say. So we need to come up with a, so this is a set. We need to take two things from V and return, so input is two things, a pair of things from V, and return a member of V, a unique member of V. So that tells me that I am taking a function. So I am taking a function and that is a binary operation. Remember, that was one of the last exercises. So this is a binary operation. Okay? We usually denote this, say, let's denote it by, let this function be written as box. So we take it and we usually write it like this. It's called an infix notation, which is very pleasing. Okay? Now, the binary operation is said to be okay, I need this, be commutative. If it is said to be associative. This is again carrying from last time's exercise.
Sorry, sir. No, excuse me. Okay, I just want to get something. So before the previous example with S, you were showing us the elements of a set, and I suppose you're applying the axioms to the elements of a set. Are you now moving into basically functions in the context of functions here?
Yes. So as I explained,
yeah,
it forces us to the notion of a binary operation. What we are doing.
Okay.
So that's why we need to look into these binary operations in isolation first.
Okay.
And some names given to a binary operation. Let's see examples. Let's take the set n of natural numbers. If I take plus to mean addition of natural numbers, it's a binary operation. Okay? It is commutative, as we know. Associative? Yes. It has an identity. 0. My natural numbers start from 0. So, okay? So it has an identity. Right? If we take to be the usual multiplication of natural numbers, do all this hold good? It's commutative. It's associative. What is the identity? 1. So over here, it's commutative. Associative. And the identity is 0. Over here, it's still the same. Here it is 1. If I take subtraction of two natural numbers, the binary operation with which property is old?
Not sure. Natural numbers don't look negative.
Good. So it is not a binary operation at all, because you have nothing to take this to. It's not defined. It's -1. It's no more in, yeah? So it is not a binary operation at all. Good. Okay? On the other hand, I need some space. Okay? Let me take the reals. And this being minus now. That's a binary operation. Is it commutative? Yeah? Let's see. 2 minus 3 is -1. 3 minus 2 is 1. I've taken minus. What you are thinking is 2 minus 3 is 2 plus minus 3. No. Okay? So this is not commutative. So every binary operation need not be commutative. Okay? It is not associative also. Okay? It's not associative also. So every binary operation need not be commutative, need not be associative. Okay? Suppose if I take the reals which are positive, and I take my operation to be addition. Yes. Okay, let's try. Associative means every one of those, right? So let's try. 2 minus 3 minus 4. This is 2 minus 1. This is 3. And 2 minus 3 minus 4. This is -1 minus 4. And what is this? Okay? Alright. Now, let's take positive reals with addition. Commutative? Associative? Yes? Does it have an identity? No. Because it's positive reals, so it is commutative. Associative, but does not have an identity. So you can see, so that was the intention of one of the last exercises in the first self-assessment, for you to give examples of binary operations. You take these three properties, so you should be able to make a table of all possible choices of ticks and crosses. Okay? So you see, it's quite interesting. Yeah? Now, suppose is a binary operation on V with an identity. We say that Y in V has an inverse if there exists a Z in V such that so even if, okay, so this is the kind of, so for instance, if we have this one, negative, it is not commutative, it is not associative, but it has an identity. Does it? 2, no, it doesn't. 2 minus 0 is 0, but 0 minus 2 is not 2. Sorry, 2 minus 0 is 2, but 0 minus 2 is not 2. Yeah? So it doesn't even have an identity also. Okay? Good. Now, let's have a look over here. When I take, in any one of these cases, in both these cases, right? It is commutative, associative, and it has an identity. But no natural number has an inverse with respect to addition. Right? Because what will be an addition of a natural number? N will have an inverse if there is an n, so that n plus n is 0. That n has to be negative. Right? So it's not there. With multiplication, for n there will be an inverse if there is an n, so that n times n is 1. Again, it's not possible. Okay? So it doesn't have. Okay? But if I take this example, say, if I take the integers, if I take my integers and I take my binary operation to be addition, It is commutative, associative, and it has negative, inverse, right? It has inverse. So, every element has inverse. Similarly, if I take the rationals, this to be multiplication, commutative, yeah.
Okay. So you're saying an inverse is based on an identity.
Correct.
Depending on the operation.
Yes. Yes. So an operation, we cannot say about an inverse of an operation. It has to have an identity first, before we can speak of an inverse. Okay? Good. Now, let's take rationals with multiplication. Commutative, associative, what's the identity? Huh? Rationals, the last one. With multiplication. It's commutative, associative. Does it have an identity? Huh? What is it? Yes, it has got 0, but the operation is multiplication. What's the identity? 1. Right? Does it have an inverse? Yes. Why no? 1. Correct. Yes. You see, so only over here, the identity is 1. And every non-zero rational has an inverse. The moment you take 0, there is no inverse. So only the non-zeros have. Okay? But if you take non-zero rationals, then everyone has an inverse, right? So the case is that it could be that the operation is very nice. It is commutative, it is associative, it has an identity, but every element may not have an inverse. Okay? Only some might. Okay? Alright. So, now question comes, as he said, the inverse is always with respect to an identity. Right? This is unique.
Sorry, sir.
Yes.
On the natural numbers.
Yes.
Yeah. What's the identity there?
With respect to which one? Which operation?
With respect to natural numbers, the addition of natural numbers, I'm just trying to think. Yeah, I'm just trying to go through it over my head, and I'm missing something.
No. There is a convention. Few people do not consider 0 to be natural, and few do. I belong to the last list. I do consider 0 to be a natural number. Okay. So my natural numbers start from 0. So 0 has an identity. So the natural numbers have an identity with respect to addition.
Okay.
And that's 0.
Okay.
Yes.
So the real numbers, the addition, why does it not have an identity?
No, it's not reals. It is positive reals.
Positive real.
Right? Because you have taken away the 0. Okay. So now, the question is the identity unique? Yes, it is. Let's see. And the proof is, so the identity, so here is the fact. So, I write a big name like this. Let's say fact. So T1. If a binary operation has an identity, then it is unique. Irrespective of whether it is commutative or associative or whatever, the fact that it has an identity forces it to be unique. Okay? So you cannot have two identities for a single binary operation.
Does it depend on the operation?
Yes, the identity is always for an operation. As we saw, the reals with the multiplication, identity is 1. The reals with addition, the identity is 0. Numbers are different, right? I didn't say unique in this way, because the identity depends on the operation. Alright? So the moment you tell me that a binary operation is having an identity, remember, you started off with that binary operation, and you told me that it has an identity. That identity is unique. You cannot have two zeros. Okay? So in some sense, it's a very, very special element. Okay? So let's see. Why? And, well, here is the proof. Let, if possible, E and E prime be two elements which are both identities, elements for the binary operation. Okay, so what does it mean? So therefore, for any x and you'll realize from this proof that mathematics is in general very simple. No. Okay, that is one of the things that I'll try and convince you as we go towards the end of this course. It is very, very simple. It is nothing complicated. Okay? From any stage, let me pronounce this slogan. At any stage, you try to see what you are given, try to see where you have to go, okay, and choose the simplest path. Okay? The simplest path. And that will give you the answer. Okay. So now let's see. You have told me for every x you have these two kinds of equations. And you have given me these two elements. So what is the simplest part? So therefore, I consider this. Now, from double star, this has to be E. Right? This is from double star. From single star, this has to be E prime. That's it.
Sorry, sir. Hello?
Hello, yes,
Excuse me.
yes.
Excuse me, sir.
Yes, please go on.
The single star, is it the definition now for the identity? Is that a definition that you're applying though?
Yes. From definition, since E is an identity, the single star equation solved.
Okay.
And since you have told me E prime is an identity, the double star equation solved.
And the double star, what definition is that?
Wait, look back into the definition of an identity. It says identity is an element for which these expressions, E shall be an identity when for every x star holds.
Okay.
So E prime is an identity, since you have told me, double star must hold for every element. Okay?
Okay.
You started off with the fact that E and E prime are both identity elements. Right? That's the